Greeting to Doctor and everyone. We are Group D from Section 1. Today, we are going to present about the experiment electromagnetic motor. This is our team member, Kek Da Quan, Marissa, Chia, Sharol, Khor Jia Ee, and me, Leez. Our experiment will be based on 3 parts: experiment video, theory explanation, and application. Hi everyone, now we are going to do our experiment. So here is our material needed: copper wire, battery, and magnet.
So our copper wire will be shaped into something like this, and now I'm going to put on it.
Next, we will move on to the introduction of magnetic fields. Electric fields and magnetic fields are interconnected. Magnetic field is a force field generated by moving electric charges, commonly produced by magnets or electric currents. Its influence extends far and wide, affecting the behavior of objects and particles within its reach. The interaction between magnetic fields and electric currents shape the behavior of charged particles, creating captivating phenomena such as electromagnetic induction and the generation of electrical power. Maxwell's equations describe the behavior of electric and magnetic fields and their interactions with charges and currents. There are Gauss's law for electric and magnetic fields, Faraday's law for electromagnetic induction, Ampere-Maxwell law of changing electric field to the magnetic field. Not only that, the generation of electromagnetic waves states that when an alternating current flows through a conductor, it creates a changing magnetic field that will generate an oscillating electric field. The combination of these oscillating electric and magnetic fields propagates through space as electromagnetic waves.
We know how to make a homopolar motor from previous experiment video, but what is the behind theory of the experiment we just conducted together? Homopolar motor is a type of electrical motor which causes a continuous circular motion that was engineered by the circular magnetic force around a wire, and it is driven by Lorentz force. Lorentz force is a fundamental concept in electromagnetism that describes the force experienced by a charged particle moving in an electric and magnetic field. It is named after the Dutch physicist Hendrik Lorentz. As the current flowing through the wire, it will generate a magnetic field, while the magnet placed on the end of the battery generates its own magnetic field when the wire with its flow of charge will pass through. When they interact with each other, these two magnetic fields will generate Lorentz force. As the current travels perpendicular to the magnetic field, Lorentz force is exerted on the conductor, which is perpendicular to both the direction of the magnetic field and the current, thus generating spinning motion. Now we can have a better vision and understanding with the formula of Lorentz force. It is shown that the force exerted on a charged particle in an electric and magnetic field is equal to the summation of multiplication of the charge with the electric field and the multiplication of charge with the cross product of magnetic field. For electric force, the direction of the charge is same as the direction of electric field. On the other hand, for magnetic force, the charge experiences no force when it stays stationary, but it experiences force when it is moving. The force exerted by a magnetic field on a moving charged particle causes it to move in a circular path. We can use left-hand rule and right-hand rule to determine the direction of the particle after pushing by the force. The left-hand rule is for the negatively charged particle, while the right-hand rule is for the positively charged particle. Our thumb represents the moving direction of the particle, index finger represents the direction of the magnetic field, while middle finger represents the magnetic force exerted, and all components are perpendicular with each other. Assuming a negatively charged particle is moving across the magnetic field from the left to the right, and the magnetic field is going into the screen. By pointing our thumb to the right index finger into the screen, we can see that our middle finger, which represents the magnetic force, is pointing downwards. Thus, Instead of going straight to the right, it goes slightly down due to the force. As the scenery continues, it generates a rotational force. By putting this theory to our experiment, this wire spins due to the rotational force. Thank you, and I'll pass it to the next member.
Now, I will explain how electromagnetism can help us in our daily life. Electromagnetism is widely used in various applications. For example, in electrical appliances and electronics. Almost all electrical appliances and electronic devices we use in our daily lives rely on electromagnetism. They can be found in many household appliances such as fans, televisions, refrigerators, washing machines, and many more. Current flowing through the wire create magnetic fields that enable the motors, transformers, and other components to work. Besides, there are also applications of electromagnetism in the medical field. Magnetic field and radio waves are used in MRI, magnetic resonance imaging, to produce detailed image of the internal structures of human body. The images are constructed through the interaction of powerful electromagnets with hydrogen atoms in the body. This non-invasive medical imaging can be used to examine almost any part of the body, allowing doctors to diagnose and monitor a wide range of medical conditions. The last applications of electromagnetism is in telecommunications. Electromagnetic waves such as radio waves and microwaves are utilized for modern communication systems. For example, mobile phones and Wi-Fi networks use electromagnetic waves to transmit and receive signals. Nowadays, we are able to communicate wirelessly over long distances with the help of these waves. All in all, electromagnetic principles and technology have a significant impact on us as it revolutionized the way we live, communicate, and access healthcare. This is all from our group. Thank you.